Since the beginning of the 2022 season, a rearward-facing suspension opening at the Red Bull caught our attention. Something like this is not happening accidentally in F1, and the guess was that Red Bull is using this outlet to blow air towards the beam wing to generate more downforce. That wouldn't be a surprise, since Adrian Newey likes to make designs look like something else to cover their real purpose. At the same time, Red Bull showed outstanding performance in both high downforce and low drag on the straights. With updates and the new car in 2023, the suspension moved, but the outlet was still there. So although it was first called suspension opening, now it wasn't anymore, which supported the theory Red Bull is doing something else here. And also external aerodynamics is pretty limited in F1, but internal aerodynamics has less limits. So it would make sense that teams try to find performance underneath the bodywork. I already released videos explaining the potential system in the past, but now Afonso Lancos at Brookes University was analyzing and designing such a system for over a year, and today we would like to present the results to you. Now Afonso will tell you a bit more about his work.
To give you a bit of a background, in the beginning of the 2022 season, it was possible to see a surprisingly large rear suspension opening on the Red Bull's car. This rearward-facing suspension opening, located on the forward leg of the rear wishbone, was commonly seen in the 2022 grid, but never with this size. One of the first thoughts was that this opening could be linked to the radiator outlet, but due to the height of the opening, this idea was quickly discarded. Additionally, since the outlet is pointing towards the underside of the beam wing, this air cannot be a low energy flow, as this will affect the rear aerodynamic performance. After the suspension wishbone moved slightly down, this indicated that the opening was there as an outlet for a fluid, possibly to improve the rear aerodynamic performance. As the height of the supposed outlet is at the height of the rear of the radiator duct, it was speculated that the system was being used to send high velocity flow through that opening. If we look at the whole sidepod and outlet system, we can understand how this concept might have worked. When air gets in the sidepod, the resistance from the radiator forces it to downwash, creating a high pressure region on the rear of the duct. When looking at the location at the suspension outlet and the rear of the sidepod duct, it is clear that this could be connected to form a high velocity jet, since there is high pressure on one side and low pressure on the other. So let's dive further into the theoretical basis of this concept. The first theoretical basis of this concept is the conservation of mass flow rate, which states that the mass flow of a fluid is constant unless there is a mass loss or gained in the system. In this case, if we consider m to be mass flow rate, m2 plus m3 equals m1, since the air that comes in the sidepod will either go through the radiator or through the bypass to be ejected at the rear of the car. The second principle being studied is the Bernoulli principle, which relates to the cross-section area, flow speed, and density. If we compare point 1 to point 2 and we assume that density is the same, we can assume that the velocity at point 2 will be higher since the area is smaller. Nevertheless, it was found that the Bernoulli effects are overwhelmed by the viscosity behavior of the fluid. As Poissier's law states, the resistance of the flow in a tubular domain is proportional to the radius and length of the tube, as well as the viscosity of the flow. Thus, the percentage of mass flow through the bypass is proportional to the ability of the system to overcome the bypass resistance. In the equation on the left, we can see that the volumetric flow is equal to P2 minus P1 over resistance, which means that the pressure difference between the inlet and outlet of the bypass is crucial to overcoming the viscous resistance. The resistance mentioned on the left can be seen again on the right, related to the length of the bypass, its radius, and viscosity of the fluid.
So to summarize that, two models have been built. First, a smaller model for the internal flow to see if the system works at all, and to fine-tune the resistance of the radiator net to realistic values. Here, we could see that at the end of the radiator duct is higher pressure, so that would be a good starting point for a bypass. But the more air goes through the bypass, the less air goes through the radiator, and that means less cooling. So Afonso had to find the sweet spot. How big does the bypass have to be to still provide decent flow, and how much cooling do you lose at this point? Straight bypass tubes with different diameters have been designed, and you can see their effects here. Problem for the smaller tubes was the internal boundary layer, which creates too much resistance. But for the bigger tubes with a radius of 15 and 20 mm, decent mass flow could be generated. And of course, the more air flows through the bypass, the less goes through the radiator. So, after establishing the internal basic mechanism, Afonso shifted to a bigger, more complex simulation including the external aerodynamics of the car, which meant designing the rear end of the car. Important was now to find out how much mass flow and which velocity of the bypass flow is necessary to see a significant aerodynamic effect. But also the bypass outlet position was important, and so 4 different positions have been analyzed. And you can see that the most inner outlet, number 1, and the lowest outlet, number 4, show the biggest effects. Also, you can clearly see the differences between the 4 different bypass diameters. The colors show you the flow velocity, and the more red it is under the beam wing, the faster is the flow there, which means lower pressure, which means more downforce. Also, keep in mind that the beam wing sits right above the diffuser outlet, so this lower pressure will help the diffuser to work harder. Outlet 4, which showed good results before, is pointing at the lower side of the beam wing and hence accelerating the flow underneath the wing. That's the reason why it shows the biggest downforce increase. In the end, for the whole car we could see some interesting effects. The bypass is not just increasing the overall downforce by 1.3%, it's also reducing drag by 0.5%. That might not sound much, but if you imagine that an F1 car is producing around 1000 kg of downforce in medium speed corners, this would be 13 kg more downforce. And the fact that downforce is increasing and drag slightly reducing shows you that the aerodynamic efficiency goes up, and all that for 8.8% less cooling. Of course, these are all simplified models, but it shows you that the general concept of a sidepod bypass works. So this system doesn't just help you to increase downforce in a straight line, it also helps you to collect clean air in the middle of the car, in a corner, and guide it to where you want it at the back. So it also helps you in slower corners, to get clean air on the beam wing, which is then supporting floor and rear wing. Another effect which hasn't been simulated yet is the effect to use the exhaust primaries to heat up the flow on the way back. Mass flow would stay the same, but because of the temperature increase, density would drop and we would get more volume flow, so faster flow through the bypass. So that's another interesting detail to look at. And this system can be used for 2 different things. We can blow air to the beam wing to increase downforce, but we can also design the wing on the edge, so that if we blow additional air to it on the straights, flow on the beam wing will separate and we could have a big drag advantage. So I would like to thank Afonso and Oxford Brookes University for the cooperation in this project, and I hope you liked this little insight into F1 engineering. If you're interested in working in F1 as well, remember Andretti is hiring massively now, check out my online courses which prepare you for a career in F1 and give you invaluable advantages in your interviews. See you at the next video.